Hello and welcome to the Classical Assumptions video tutorial for ECON 4650. The objectives of this video tutorial are that you'll be able to create data to illustrate classical assumptions relating to the properties of the error term epsilon, to create data to illustrate classical assumptions relating to the sampling distribution of beta hat, and that you'll become familiar with running iterative or repeated regressions in R and extracting data from these. For this module on classical assumptions, we're basically going to generate some data that either illustrate a violation of some of these classical assumptions. The chapter is essentially an overview of this, and we are going to work with a few of these with data that we create in R. So the first one that we're going to demonstrate is the second classical assumption, which is that the error term epsilon has a zero population mean. And we know that the constant term in the equation, beta 0, will keep the mean of epsilon near 0 because it compensates for the fixed portion of y that the independent variables cannot explain. And essentially, we know that the value of the error term for each observation is determined by chance. And when the entire population of possible values for the stochastic or random error term is considered, we know that the average value of that population is going to be 0. And it's going to become clearer as we increase the sample size. So let's go ahead and demonstrate this with the simple regression that we generate in R. So we're going to use the equation y equal to 50 plus x plus epsilon. And so in this equation, beta 1 is going to be equal to 0 because we're simply demonstrating the properties of the error term epsilon. So that being said, let's get to work here, and we're going to create data for x by drawing 42 numbers from a uniform random distribution from -50 to 50, and we can do this using the runIf command. So we're going to set our seed so that we can reproduce these results, and we're going to say x is 50 minus 100 times runIf 42. And looking at summary of x, shows our data that we just created there. And now let's generate the numbers for y with beta 0 being 50 as we described before. And we're going to draw the errors from a standard normal distribution with that rnorm command. So we're going to say set.seed 200 and y is 50 plus 0 times x plus rnorm 42. And let's draw a histogram of y. It should look normal. Giant histogram there. Let's resize this. And there shouldn't be any patterning between x and y because there's no relationship between them. So let's say plot of x and y. Not a lot to look at there. But we want to look at the errors. So let's run a linear regression and pull the errors from that. So we're going to call it model 1. And we're going to say lm of y tilde x. And we're going to plot. We're going to do a density plot of these residuals. So we're going to say density, and we want to pull out the residuals from model 1. So we're going to say model 1 $sign residuals. And so here we've got our kernel density plot, and we can see that the residuals are approximately distributed around 0. It's not a perfect distribution, but given our sample size, that's looking pretty good. And we can compare this with the graph, or with figure 1 on page 71 of the text, called an error term distribution with mean of 0. So we created the errors given the rnorm command, which by default is going to use a mean of 0 and a standard deviation of 1, so it's not too surprising. But let's draw even more y values to get our hypothetical error term even closer to the real unexplained uh, parts of the y's in our regression. And before we do that, let's draw out the mean. Since it is supposed to be close to 0, let's just check what it is. And we're going to say residuals again. And we see there it's an extremely small negative number. So that's pretty close to 0, pretty good. Let's see how that looks when we increase the sample size now. So again, we're going to do that. And we're going to say x dot 2 is going to be our new x data, and it's going to be 50 minus 100 times runif. We're going to say 1002, and actually we're going to say 10,002. Let's give us big size there. And our y variable is going to be equal to 50 plus 0 times x2 plus r norm 10,002. And we're going to create another model, model.2, and we're going to say lm of y dot 2 tilde x dot 2, and we're going to plot the density plot of that, so of those residuals. So we're going to say density model 2 residuals. And we see there that having increased our sample or our draw significantly to 10,000, we have a much clearer look at the distribution, and it does look much more like a standard normal distribution. And if we find the mean of that, we'll expect it to be very similar to 0 or close to 0, and hopefully closer than the last one. So let's look at mean of model dot $2 residuals, and pull that out, and it has gotten closer to 0, as it is once again a negative and smaller number than what we had before. So as the sample size grows, the residual density plot shows that the normal distribution of error terms, which again we designated intentionally, is going to become more and more clear. And as in the first example, the mean of the residuals is very close to 0, just a very small negative number. So the next classical assumption we're going to demonstrate is the fifth one, which is that the error term has constant variance. So the actual values of the error term are again not directly observable, but the lack of a constant variance for the distribution of the error term causes OLS basically to generate inaccurate estimates of the standard error of the coefficients. And the violation of this assumption is referred to as heteroskedasticity. And we're going to illustrate this by generating data which has variance related to the explanatory variable. So we're going to change the code a bit so we can calculate the standard deviation of the error terms with non-negative numbers, which is incredibly important. So we're going to say small x equal to, we're going to create a sequence from 1 to 42 with a length of 42. And we're going to create a y, or we're going to create our y's, and we're going to say again it's equal to 50 plus 0 times x, small x, plus r norm and length of x. We want to tell it to create the same number of y's as we have x's, with the standard deviation equal to 0.1 1 times x. So this is going to create some heteroscedasticity for us. And then we're going to run that model. We're going to say model is lm of y on x, or x on y. And we're going to plot those residuals and see what we get. Again, we're going to use the $sign to pull the residuals out of that model. And we see that the residuals there are kind of increasing in spread, which is this is kind of a sign as their variance increases with relation to x. It's going to be a pretty clear sign of heteroscedasticity. And so this is something that you're going to want to pay attention to when you're running your regression. You can do a residual plot like this, and if you see this kind of pattern, then you know you've got heteroscedasticity, and we're going to learn how to deal with that in the next module or in future modules. The heteroscedasticity could also look opposite of this and be increasing in the beginning, and then the variance is decreasing in the errors as it goes along. So just anything that's not like a constant variance with the residuals. Another way to show this is if you plot the squared residuals. Just kind of give you more idea of the absolute variance. You can see that there's obviously some increase going on there. And again, this is not going to result in biased parameter estimates, but the standard error will be biased. It'll be inflated compared to the true estimate. And the OLS estimators will not be blue, meaning that while the parameter estimates may not be biased, the variance is no longer going to be as small as possible. Basically, we just said the same thing twice. And for illustration of this, we can run a similar regression equation without the error variance, and you're probably going to see similar estimates with a smaller standard error. So let's run the summary of this model so we have something to compare our next one to. You can note the size of the standard errors there. And so now if we want to run another model without this heteroscedasticity, we'll say y dot 2 equal to 50, we'll say 50 plus 0 times x plus r norm length of 40 of x with the standard deviation of something constant like 0.1. And then if you run this new model, and plot the residuals, that is, you're going to see a much different picture than we saw last time, right? So there's no clear increase or decrease in variance of the errors with relation to x there. And again, we can run the squares of those residuals. For a more clear picture there. So it's not clear that it's increasing with x. I mean, there is some variance there as we'd expect, but it doesn't seem to be directly related to the change in the x variable as it was last time. And let's run a summary of that. And we can see that our standard errors in the model without heteroscedasticity are actually much lower than the ones with. So you can compare those, kind of illustrating our point there. Now we're going to look at the sampling distribution of beta hat. So we know that each different sample of data produces a different estimate of beta, which we call beta hat. And the probability distribution of these beta hat values across different samples is called the sampling distribution of beta hat. Okay, so the first thing we want to do is look at the properties of the mean of the sampling distribution of beta hat. So an estimator, beta hat, is unbiased if its sampling distribution has its expected value as the true value of beta, right? So let's kind of dive in here, and we're going to illustrate this by returning to our first model, Model 1. So if you recall, summary of Model 1, we see there that beta 1 hat, which is here, is pretty darn close to 0, which is what the true value of beta was because we set it as 0. And if we change our model to y equals 50 plus 5x plus epsilon, then you could find something similar. Let's set the seed again. It's not necessarily something you have to do if you're still in the same session, but if you're in a new session or you've changed your seed, you want to make sure that that's still set to what we want it to. And we're going to say y2 as 50 plus 5 times x plus our norm of 42. And then you can use the lm command to estimate beta. So we'll say model 2 is lm of y2 x, and you look at a summary of that model. You'll notice that it estimated beta pretty close to 5 there, right? So we can repeat this experiment of drawing values of y and estimating beta over and over again and see what the distribution of our estimates of beta hat looks like. So to do this, we're going to set up some placeholders for our estimate of beta, as well as their standard errors and t-values, which is kind of a preview of what we're going to get into in the next module. We're going to take 1,000 draws, estimate 1,000 regressions, and look at the estimates of beta which result. And in this example, as before, n is going to be equal to 42, so k is going to be equal to 2, so n minus k is 40, right? So we're saying that we have 40 degrees of freedom. And we're going to repeat this exercise 1,000 times, and we're going to generate the y values for beta equal to 0 and the intercept equal to 5, and the error term drawn from a standard normal distribution. So here we go. So we're going to say beta is called rep 0 to 1,000. So we're basically telling R to create. Actually, I think rep will create a matrix, but we're telling R to create like a placeholder that we can save the data for the 1,000 draws of beta that we're about to create. So that's what we're doing with that. SE beta. For the standard error. ST beta. And so that we can calculate our t values. And now we're going to tell it to run a regression, dump the data into those placeholders that we created, and repeat it 1,000 times. So we're going to say for I in 1 to 1,000. So I being the basically the variable which represents whatever current count we are on. And we're going to do a open bracket and delete that second one, hit enter, and start typing in your lines here. So, and if you're in Windows, you shouldn't have to delete that second one. So we're going to say y is 5 plus 0 times x plus R norm, R norm 42, and the model is going to be just lm of y and x. It's capital X. And we're going to tell it how to populate the beta. So we're going to say beta of I. So for each iteration that it runs, it's going to put the beta coefficient in there, which we can grab by saying model $coef 2, right? So this is the so the second coefficient is going to be the slope or beta hat estimate that we are looking for. Coef 1 would be the intercept. And we're going to say SE beta of I equal to summary model. From the summary, we're going to pull out coefficients for, and that's going to grab the standard error from the model, and ST beta of I, which can calculate a bunch of t values by taking beta of any given run divided by the SE beta of the same run. So taking the beta and dividing it by the standard error of that beta, and we'll be looking more at the t-scores in the next module. So it didn't give us an error, which is a great sign. So let's look at the summary of beta hat, which will be kind of our sampling distribution. So summary of beta, and it looks like the highest value we obtained was 0.0204 or 244, and the smallest value was negative 0.0214. So those are all actually grouped pretty tightly around 0, which we know as our true value. And we can look at a density plot or smooth histogram of our 1000 estimate. So we'll say plot density beta, and we'll title it. You can give it a title by saying main, and it's called beta hats in quotes. And there we have it. So that is a plot, a density plot of our sampling distribution. So we ran this linear regression 1000 times and grabbed 1000 beta hat 1 estimates, and that's what that turned out like. So as you can see, if you grab a significant amount, it really does end up being fairly centered around 0. Which again, we could kind of expect because we dictated what the errors would be with the rnorm command, but this is just kind of an illustration of what you can do with R in terms of having it run 1000 regressions end on end and grabbing the beta values for you there. So it's kind of a illustration of the sampling distribution. And the last thing we want to do is talk about the properties of the variance. So for the properties of variance of the sampling distribution of beta hat, I'd like us to recall the models that we were running when we were talking about the properties of the error term epsilon, because we're going to use those to examine variance for estimators as well. So if we go in and say summary of model 1, and we take a look at the standard error of the beta hat 1 estimate here, it's pretty low. It's a 0.005, and remember that was a model where we had specified that the relationship between x and y was 0, so that's pretty good. It's close. And then we can recreate the model that we ran that was the same specification but ran 1002 times. So, or actually, it ran 10,000 two times. Unfortunately, we renamed it, or we renamed Model 2 as some other model during the course. So let's just recreate that real quick. We're going to say our Model 2 is going to be those values LM Y2 on your left hand side, y.2 and squiggly and capital X dot 2. And if we look at the summary of Model 2, we'll see that the standard error is a much smaller number here, given that we've kept the specification of the model the same. We've just increased the size of the sample by a significant amount. So this is just illustrating the idea in terms of properties of the variance that if you increase your sample size, you're going to get a lower standard error, which is basically going to increase the likelihood that your estimated coefficient will actually be equal to the true coefficient. Thank you, and that's the end of this video tutorial. Moving on, assignment 3 is available in Canvas in the classical assumptions module.